Well, good afternoon, Calculus 2 students. Um, I actually posted the link to the lecture that we had on Monday. I know not everybody could make it. That was just the beginning of the winter weather that we had. And I actually had posted it in a class that was not your class. So I apologize for that. I have actually moved the post to week 5 so you have access to that. I'm sure some of my pre-calculus students thought, well, this is interesting. A lecture on center of mass. I don't even know what an integral is. So I was doing some more lectures for my pre-calculus students. And when I went to add those to their Blackboard site, I noticed that I had done that. So some of you were able to make the lecture, but the complete lecture is up so that you can utilize the content and complete your WebAssign. This is the first day that I've had that I have been with Power. Uh, I did receive Power late last night, and I was able to change the due dates for the WebAssign. But it such a glorious thing to have power and be able to do what you need to do. So I hope everybody's safe and that you're in a situation where you can actually do your work and have some comfort. So let's move forward. Um, what what I want to start with, remember I told you that we were going to review some integration from our past life in Calculus 1. Section 1 of Chapter 8 is very straightforward, and I want to go over several examples, but I don't think you'll find it to be difficult at all. The work that we did with the inverse trig forms actually got you back into the integrating mode. And a lot of the integrals we've done with the applications have kept you in that. So I think you'll find section 1 of chapter 8 to be very straightforward. So what I wanted to do was do some more with the center of mass, and also to share an example with you that was requested by one of your colleagues. I thought it was a good example from work that may benefit you. So we'll start with that, do a couple more examples from the center of mass, and then conclude with some of the review of the integration process. So this will set us up for the next week that we have after the storm to begin with integration by parts. So again, take time to go through these lectures and to get the content that you need so we can stay on schedule. So let me go ahead and share my screen. Now, this particular example was a work example, and it's in your WebAssign. And I thought it was good. I went ahead and wrote up the example, and I thought this would be good to share with all of my students. Now, again, the center of mass and the work examples are very much related. I think the center of mass is a little bit more complicated, but certainly doable. But in this particular problem, you had a tank, a cylindrical tank in the bed of a truck lying horizontally. So the axis was horizontal, and the actual tank is used to fuel tractors. And the tractor tank is 5 feet above the top of the tank in the bed of the truck. And so what you want to do is empty the entire contents of the tank into the tractor tank. So again, this is moving liquids just like we did and we've done several times in the work examples. And in this particular problem, the weight density of the liquid or the gas was 6,600 newtons per cubic meter. And again, we're given in this particular case that we have a tank that has diameter 3. So that means we have a radius of 3/2, and the breadth of the tank, that is the length of the tank, is 2 meters. And so basically what we want to do is use that geometry to see what kind of calculus we need to do to move the contents of the tank into that of the tractor. So I've written this up in a very simple way. This will look like I've pretty much done all the problems. And I also have this problem worked out in the lecture notes. So there's another example that you can see. So what I did is that I just took a cross section of the tank and put it right at the origin. So again, the diameter is 3, so this gives you a radius of 3/2. Now, again, when you look at this configuration, we want to use some really nice calculus properties like we've done before, like when we did the torus. So again, note that in this case, y will run from -3/2 to +3/2. So we get that from the outset. And plus, we have this circle, and we certainly want y to be independent. So we basically write the circle in terms of y. So if we think of the positive arc right here, that would be x equal the square root of 9/4 minus y squared, just like we would have for the arc of a circle. And then, of course, if we are 5 meters above the actual top of the tank, basically from the origin of our coordinate system, that'll put us at 5 plus 3/2 or 13/2. So all we need to do now is simply figure out the volume of the slab of liquid. So what we can do is take a particular y and then look at the distance all the way across. Now notice here, this will just be the delta y, the thickness of the slab. And then of course the distance across will just be twice the radical. So we want to take in the actual positive arc and the negative arc. Okay, so that'll give us 2 times the square root of 9/4 minus y squared. Now, what we want to do is write down the volume. Again, the actual tank is 2 meters long, and we have delta V will now be the length times the breadth times the thickness. So that just gives us, in this particular case, 4 times the square root of 9/4 minus y squared square rooted times the delta y. Now, of course, the force will just be the volume times the weight density. So we just multiply this expression by rho, again, not P, rho. And again, I'll just fit the rho in between the 4 and the radical. And then to get the actual work to move this slab of liquid, we have to move the requisite distance, which in this case would be up to the tractor tank, which would be 13/2 minus y, the y given to be between -3/2 and 3/2. So this is a construct that we have seen before. Again, once you start doing the applications in calculus, the techniques do repeat, and you use them over and over. So now, as I've noted here, we have the force times the distance, and I've just noted the distance right here. Now, in order to compute the work to empty the contents of the tank, we would need to integrate from -3/2 to 3/2 this expression. And so now in the integral, the deltas become the d's, and then of course we just have all the same algebra that we have here. Now, what's nice about this should remind you a lot of the torus example. We've got the same geometry going on. So now for the first integral, or the first expression here, we're going to have 4 rho times 13/2 times the radical, which we write first. So we're going to distribute these two numbers. And then we're going to have 4 rho times the negative y times the radical to get this. So we have one integral here. Now, of course, we're going to use the linearity of the integral to break this up into 2 pieces. So what I wanted to do now is to go ahead and factor the 4 rho and the 13/2 to give us 4 rho times 13/2. And then, of course, we integrate from -3/2 to 3/2 the radical. And I'll say more about this. Let me just go ahead and set this one up. When we do this one in particular, we have y times the radical from the -3/2 to 3/2 times the -4 rho. Now, of course, this is the area under the curve above the y-axis, looking at this right here, this piece right here. That's just half the area of the circle. So this portion here, we know through geometry. Now, another thing that we've used before, and this is a very nice application of that also, we have y times the square root. Notice this is an odd function, because if we were to replace the y with the additive inverse of y, we would get the negative of this integrand. And of course, you know, what we're seeing here is that the domain is symmetric also. It's just the interval of integration. So we know the odd function on the symmetric interval that's integrated has a value of 0. So again, we get to use all of these nice results from calculus that make what would be a very maybe more difficult problem quite doable. And of course would require more techniques that we will learn in the next chapter. So now here we have 1/2 the area of the circle, the radius being 3/2, we square that, multiply by pi, and then hit with the factor of 1/2 because it's just half of the circle. And then of course we have the 4 rho times 13 divided by 2. And then of course this just zeroes out, so we're done. So now all we have to do is navigate the arithmetic here. Notice, if you will, we can go ahead and reduce the 4 over 2 to 2 here. So we have a rho and a 13. And then of course pi over 2 times 9/4. And now of course we can remove the 2 over and absorb that. And that's going to leave us with a rho times a 13 times a 9 pi divided by 4, which I've written here off to the left. Now we go back up to the top here to substitute the value, the weight density of the fuel. And so we get 6,600. Now, in order to retire the 4, this is clearly divisible by 4. So when you divide, of course, you get the 1, and then you get the 6, the 5, and the 0. So you get 1650 here. And so that's nice. And then, of course, we can break this up into 2 pieces. We can just hit this with a 10 and a 3. The 10 would just, of course, add another 0. And then hitting this with the 3, we can do. So we get the 0 and the 15 and the 1 in this particular case, which would give us the 49, 48 plus the 1. Now, the interesting thing about this particular problem is that if you look at it, it reminds us exactly of the volume of the torus. So you might want to compare the two, but maybe not as difficult. I don't know. Shell method, work problem. And now when we look at this, we can add these two numbers. That is the 0, we get the 5, and then we get the 9 and the 5, which gives us the 14, carry the 1, we get the 21,450 times the 9 pi. And then of course, now we can just hit all of this with a 9, and this will give us 193,050 pi, and then Newton meters. Or if you like, you can just write joules. Of course, you know this from your physics classes, which I'm sure a lot of you are taking University Physics 1 or going to be taking it. So what I wanted to note here with this particular problem is that I think the difficulty is as you start to navigate, maybe you don't notice this and you compute it, but you get something other than 0. That would be an easy place to just kind of make a mistake. And so I think this is an important construct. And again, when you have this kind of algebra that fits into the geometry, it's always good to take advantage of it. So as you work this problem, keep these steps in mind, okay? So again, what I want to do today is show you lots of good problems that will be a little bit more efficient so that you can have good content when you do your problems on WebAssign. Okay, now with the last lecture, remember I set up the problem. I set up the problem with the center of mass of the parallelogram. I did all the work for you except do the integral. So I thought, well, you know, why not go ahead and finish? So everything I've done here is basically what I did in class. So remember, if you remember from the lecture, we had the vertices 0, 0, A0, A plus B comma C, and then B comma C. And then because, remember, the rectangle is horizontal, the actual formulas for the moments about the X and Y axes flip. The definition for the center of mass does not change, but since now we have a horizontal rectangle, it does affect the formula because when we derive the formula the formula was vertical. And you're thinking, why doesn't this happen in the other problems? I've already said something about this. The center of mass involves both axes, regardless of the problem you're doing. So when you actually develop a formula with a certain disposition of rectangle, it will affect how you orient it in the problem. So that's what makes the center of mass more difficult. So now what we did, and this is exactly what I did in class. Again, if you want to look at this by turning the page, this will be even easier to get, but I tried to work through it with the um, uh, X coordinates to make it more like the college algebra. But now you see we get the same thing I told you would. So when we look at the right curve and the left curve, we have these two functions here. And so when we utilize these in the moment calculations, we're good to go. And then another thing that's nice about this, we're looking for the centroid, so to speak, just as a geometric construct. So we can just simply set the area density to be 1. And that really makes the calculus easy. And so if, instead of running the row through, we just have a 1. So a 1/2 here and then just a shadow 1. So this is always possible. However, when you're doing a generalized problem where the row is not given and it's not assumed to be 1, then you can't leave it out of the moment calculation, unfortunately. So if it's part of the problem, you have to leave it there. We're just making this assumption because we're asked to find the centroid, where we can make the assumption of a area density of 1. So now again, like I said before, the definition for center of mass right here does not change. And because we're using the geometry of the parallelogram, the actual mass is actually the area. That is, we say the area times rho, but rho being 1, we just get base times height, AC. So there's a lot of information about this problem that's very straightforward. However, this is an excellent exercise to get this in tow. And so there's another example in your WebAssign where you're actually doing an algebraic setup like I did during the lecture, where the rectangle will actually be oriented in a horizontal manner. And so you will have to make this change in your moment calculations. But it's not major. It's just, again, respecting the fact how we actually derive the formula. So when you do this, the first one that we want to do, and I've written the formulas here again, we want to do the moment about the x-axis. So this is the easy one where we just say y times the difference. So we have f of y minus g of y. And of course, again, we're integrating from 0 to c. So when we think about our original problem, y just runs from 0 to c as we have here. So it's a very, very nice problem. And you can do the exact same calculation for the centroid of a triangle. You do it exactly the same way with the horizontal rectangle. That's just so you avoid a bunch of integrals, which make the problem a lot more tedious. And so now when you look at this, what we want to do is just first, just consider the difference here, but how nice the b over cy is just absorb, as we see here. And this leaves us with an ay dy because the only thing that survives here is a. And so when we add 1 and divide by the new power, we just have a y squared over 2. And then, of course, the lower limit obliterates this, and we're just left with c. So we get ac squared over 2 minus the lower limit evaluation, which is 0, and get ac squared over 2. Okay? And the idea, again, that you get an answer that you expect. It's funny, when you do these problems, there's a certain intuition involved. And now for the moment about the y-axis, which has been flipped because of the position of the horizontal rectangle, we've got the 1/2, the row is 1, and we have the f squared minus the g squared, just like we did with the vertical rectangle for the moment about the x-axis. So we just square this. So we're going to get a b squared over c squared y squared. We're going to take the product and hit it with a 2. So that's going to be a 2ab over c times y. And then, of course, square the last term, which is a squared. And then, of course, here, this will just give us the square of this term, which is b squared over c squared times y squared. Well, another nice result, these two terms absorb. So the algebra really is very straightforward here. It's not, we've done much more tedious problems with with just plain old algebra and arithmetic. So this is not as bad as you might think. And so now we're left with the integral times the constant 1/2 from 0 to c of 2ab over c times y plus a squared. And so now we just add 1 and divide by the new power. So in this case, we have 2ab divided by c times y squared over 2, and then of course a squared y evaluated from 0 to c. Again, noting that the lower limit just gives us a 0. And then when we substitute the c, in this case, we get of course, the 2's absorb, right? We get an AB c squared over c. And here, of course, we get an a squared times the c. Again, noting the 0 here from the lower limit. And so now when we actually look at this, one of the c's absorbs here to give us ABC. Well, you know, ABC in alphabetical order. And then, of course, a squared times c times the 1/2. So now, if you will, you can just notice that we have an AC common to both to leave behind an A here. And then actually, let's see here. Oh, and I wrote these in alphabetical order. Here we leave behind the B, which I wrote here so I could still maintain it. And then, of course, here we leave behind the A. So I just flipped that around so it looked right. I'm thinking, oh, I don't know why I did that, but then I can see why I did it because I wanted to write it in alphabetical order. Now, by definition, the x-coordinate of the center of mass will be the moment about the y-axis divided by the mass. And of course, the y-coordinate of the center of mass will be the moment about the x-axis divided by the mass. And so now we go up here, moment about the y-axis, which is AC over 2 times A plus B, dividing by AC or multiplying by 1 over AC. Notice the AC is absorbed, and we just have the average of A and B, which you expected. And then, of course, for the y-coordinate, we've got the moment about the x-axis, which is AC squared divided by 2 times the 1 over the mass. That is, we reciprocate, divide by m. And notice in this particular case, the A absorbs and one of the C's absorb, and we're left with C over 2, which again is what you expected from the geometry of the situation. So we see that the actual center of mass for the parallelogram is A plus B divided by 2 for the x-coordinate and C over 2 for the y-coordinate. So I think these problems are interesting geometrically. I mean, let's face it, when we have nice objects like on the next problem, which is kind of a fun problem, but can be confusing if you don't think about it, certain center of mass can be easy to compute just because of the nature or symmetry of the object. But when you're talking about a parallelogram or a triangle, there's much more variation there. And so you have to be a little bit more subtle in how you describe it. It's going to take a lot of work. You can't just boom, intuit it in your head. Okay. So now I thought this was nice, and I thought you deserved an explanation of this. I bothered to set it up. So now you can teach your friends how to do this. Now, another WebAssign problem that I like to do, I noticed here, I put a little approximation here, basically because WebAssign asks for an approximation. And I did, usually I just leave it exact, but I went ahead and wrote that in. Lots of times as I start to do a problem, I'll think, well, I'll do it this way, or I'll change the notation. And so as you work your problems, you'll make an effort to make the notation flow, even though in mathematics, that's always something you're going to think about. Now, when you look at this particular problem, what I've set up here is from the WebAssign, you have these two nice symmetric objects. You have a square, and it's easy to find the center of mass of a square. Again, we're going to think of the centroid as center of mass in this particular case. And then we've got this circle. And what's nice, ladies and gentlemen, is that the geometry is already set up for us. We have the y-axis here, and we have the x-axis here, and the coordinates are already good for us. So now when we look at this particular problem, the only hiccup, again, we're going to set rho to be 1, but the area density of the circle is twice that of the square. So we have to note that when we actually do this problem. So I'll think of doing the mass of each of these objects and then use M. That's where I changed up my notation for the system mass. So it will be like the formulation I gave you for the last lecture. So notice now, and this is not very difficult. First thing we want to do is to note that for the center of mass here, based on this geometry, for the square, it's just the dead center of the square, which is 2, 0. And now, of course, notice we have an edge length of the square of 4. So the area of the square is just 4 squared, which is 16. And now, of course, the mass of the square would just be 1 times 16, which is 16. So very simple. Now for the circle, again, dead center of the circle would just be 6, 0, geometric center as I've written here in blue. And then now the actual area of the circle is pi r squared. So when you look at this, you see area of circle pi r squared. Again, the radius is 2, so we get 4 pi. But now remember, the area density is 2, so the mass of the circle will be twice the area, in this case, which will be 8 times pi, just using the 2 here as opposed to the 1 here. That's given in the problem, and it's easy to overlook. And so now the mass of the system would be the mass of the square plus the mass of the circle, which gives you, in this case, 16 plus, and I noted the 2 here, rewrote it to remind you, 2 times 4 pi. So that gives you 16 plus 8 pi. And if you want to factor the 8, that's just 8 times 2 plus pi. So again, that's just a way of writing maybe the mass in a convenient way for factoring and for arithmetic, but certainly not required. Now again, we're setting this up using the definitions that we used from the very beginning. That is, this is a discrete system. We just have a 2-point system because we're thinking of each of these geometric objects as having their mass confined to the point mass. It's as if the mass is right at the geometric center. And so this is a discrete system. So it's just like the very first setup that I gave you in the lecture that we did on Monday. So now what we want to see here is that the moment about the x-axis includes the distance to the x-axis, but both of these points here are on the x-axis. So this is just 0. I mean, you could look at that and say, well, that's 0. Those points live on the x-axis. So the distance to the x-axis is 0. And therefore the y-coordinate of the center of mass is the moment about the x-axis divided by the system mass, which in this case would be 0. So that's very easy. You didn't even have to do the problem to see that. You could have just said, okay, that's 0 and we're done. Let's work on the, in this case, the y-coordinate, excuse me, the x-coordinate of the center of mass. And now the y moment, or the moment about the y-axis, we have to look at the distance to the y-axis from each of these point masses. So in the first case, the 2 here gives us the distance for this particular point mass, which is 16. And then for the point mass 8 pi, the distance is clearly 6. Again, these are algebraic distances, but the way this problem is set up, they're on the positive realm, okay? So we have to abide by that. So this, in this case, if you notice, we've got a 16 in both cases. So I write that as an 8 times 2 and 8 times 2. We have a 2 left over here. And then, of course, from the 6, we have a 3. And, of course, the pi that comes along. So now when you factor, you get 16 times 2 plus 3 pi. You know how I like to factor things to death? I just do that because it tends to make the algebra and the arithmetic a little bit easier. So now when you look at the x-coordinate of the center of mass, we have the moment about the y-axis divided by the system mass, 8 times 2 plus pi. And then, of course, in this particular case, the moment about the y-axis is 16 times 2 plus 3 pi. So now what we can see is that the 8 divides into the 16 as we have it naturally written. So that's just going to give us a 2 times a 2 plus 3 pi. And what's left over on the bottom is 2 plus pi. And I went ahead and approximated this. This is 4.444 to 3 decimals, however, but this is the exact. So now when you actually write the exact geometric center of this system, it will be 2 times 2 plus 3 pi divided by the quantity 2 plus pi. And of course, the y coordinate being 0. This is not an overly difficult problem, but I thought it was interesting. If you work with the notation, you can make it very clear, and you can see how when we start with a discrete system, this is completely devoid of integrals because we have the beautiful symmetry. Okay, so that's why center of mass can be very intuitive. However, when you get objects that don't possess this beautiful symmetry, then we have to work a lot harder, as you saw in the last problem, and is the problem that I did during lecture, which had tons of algebra and tons of arithmetic in it. So indeed, the center of mass is a more difficult computation. Okay, so good, we're done with this. Now what I want to do is do some review of some integrals. Now this first page here, the first one I thought was interesting from your WebAssign, and then I make a little comment here. This is what I teach in my pre-calculus class, and I don't think any of you took me for pre-cal, so you may not have seen this formula, but we're going to use it as a substitute for the Weierstrass substitution, which is a more complicated strategy that we don't want to use unless we have to. So this first integral I thought was kind of neat. It was easy, but it was certainly something that I thought to be interesting. So we have the integral from -2 to 1 of e to the x divided by e to the 2x plus 4e to the x plus 4. And so, of course, that PDF that I sent you that had all those nice little formulas in it for the integrals and derivatives, you should use that as a reference just to make sure you've got the basic forms down. And now, of course, what we notice, we're big on perfect squares because we've done arc length. So here we just have a perfect square, which is e to the x plus 2 quantity squared. And so now when you look at this, you're thinking, well, this is add 1 divided by the new power, basically. So when we set this here, the radicand, or the actual argument of the square, as u, e to the x plus 2, du is just equal to e to the x dx, which we have here. And so now just a little cosmetic work. This is table ready. Like I say, add 1 divided by the new power. So now the new power is -1. And then, of course, we divide by -1, which is multiplication by -1. And we evaluate between -2 and 1. So now, of course, we have the negative. And of course, I wrote this without the negative power, since it's a little bit easier to evaluate. So of course, we replace x with 1, and we just get e plus 2 reciprocated. And then, of course, we replace x with -2, and we get -1 over e to the -2 plus 2. And so, if you will, you can just flip this around. Notice this negative outside will transpose everything. So now we have the e to the -2 plus 2 reciprocated minus e plus 2 reciprocated. So this is not an overly difficult problem, but it's just an algebraic construct, which we've done many times. And hopefully after doing the arc length calculations, you're really good at spotting perfect squares. Now, I had written some other stuff under this as a streamlined proof, but it was more than I wanted to say. So I continued the proof on the next page, which is very simple. I thought there's no need to add additional structure when it's not necessary. That's one thing about trigonometry. When you need the additional structure, of course, but when you can do without it, then we opt for that. So this particular problem is really nice. The first time I saw this, it may have been in a pre-calculus class, but I remember seeing this in a differential equations class as a way to combine a sine and a cosine function. So what we do is we fix the real numbers a and b. Real numbers are fixed, and we let x be a real number. Then what we do is we say, okay, it is true that a times sine x plus b times cosine x can be written as a single sine function. That is the square root of a squared plus b squared times sine of the sum argument x plus phi. Well, what's phi? Well, the tangent of phi is b over a. So we can think of this in terms of like an opposite over adjacent in a way that we look at the unit circle with the imposed right triangles. So and of course, if you think about what phi is, you just take the inverse tangent of both sides. So, phi would live, here, in the fourth quadrant and in the first quadrant. So again, trigonometry is all about reference numbers and reference angles and adjusting when necessary. But we build it based on a geometric construct. And then of course, when you get to the end of this course, we're thinking about the trig functions as an infinite series. So then you're plagued with the idea of starting with an infinite series definition of sine and cosine, which are completely legitimate. But as future engineers and physicists and all and mathematicians, you need to be able to think of the trig functions geometrically, because we see what it affords us, the ability to work in a visual manner, which otherwise would, with different definitions, would not be open to us. So what I've done here is simply make two definitions. And I was doing some of this on Wednesday when I had no power. I wrote some of these things out because I was freezing, but I just opened the window, the shades and all that, and just sat by the window and worked these, and my nose was running. But I thought, well, you know, what better way to get over the dreariness of freezing and no power than to work math problems. That gets your mind focused on something else. So now, of course, if tangent phi is b over a, we can now think of the cosine in the similar definition as a divided by the square root of a squared plus b squared. And then, of course, for sine phi, thinking in terms of the right triangle definitions as b divided by a squared plus b squared. So now we can solve for a and solve for b algebraically. So now a will just be the cosine of phi times the radical, and b will be the sine of phi times the radical. So we're thinking, there you have it, there you have it. So a sine x plus b sine x will now just be, again, we can do this, the square root of a squared plus b squared times sine x times cosine x, because now what you can see is that we have replaced, in this particular case, the a with the cosine term. And then, of course, here we replace the b with the sine term. And so we basically get the sum formula for the sine function, you know. And so again, x is taking the place of a when I write them, and phi is taking the place of b, or you can use whatever letters you like. But this is just the sum formula for the sine function. That is, this is sine of x plus phi. Of course, I can't use the a's and b's because I'm using them here. So when I teach pre-cal, I use uppercase letters for these function identities because the students get confused if I use x and y's and u's and v's. So, but again, what we see here is we have a very convenient way of writing the sum of a sine and a cosine function with fixed coefficients as a single sine function, which of course is much easier to graph. You know how to graph these in pre-cal. And so trying to graph a function as a sum is difficult, but trying to graph this is very simple. And of course, you learned that in pre-cal. So why do we care about this? Well, again, we often find the case, I looked through your book and tried to find some interesting examples. And I actually included this in the WebAssign, so I'm showing you how to do it, which is what I usually do anyway. But we see that we have what I've written here, rational expression of sine and cosine. And so normally, if we don't have something nice like this, we have to resort to a more difficult construct with the half angle formula for tangent. But since we already have this at our disposal, we can use it. So notice here, from this particular derivation here, if we have sine x plus cosine x, we have the a and b are both equal to 1. And so the square root of a squared plus b squared is just the square root of 2. And of course, tangent phi equal 1 is just what phi is pi over 4. So this is a very user-friendly setup here. So again, tangent of phi equals 1 over 1 because we have a equals 1 and b equals 1. And so, of course, that's 1 if and only if phi is the inverse tangent of 1, and that's clearly pi over 4. So again, even if you can't write this down, you can still put the expression for it and get an exact answer. But I thought this was nice because all of the computations are user-friendly. So now when you look at this, you're thinking, okay, this is uncomfortable. This is simple because we can reciprocate it. So now we have the integral of 1 over sine x plus cosine x, where now we replace the sine x plus cosine x with the root 2 sine of x plus pi over 4. And now, of course, just factor the 1 over root 2. And of course, 1 over sine is just cosecant. So we're thinking, okay, calculus 1. Let's remind ourselves. I'll write this down here. We have cosecant of u du, and there's several ways to write this. This will be the negative of the natural log of cosecant u plus cotangent u. And of course, plus a constant. Now, of course, if you want to run the negative end, run it up as a power and then reciprocate, you can also write this way. Once you reciprocate, you get cosecant u minus cotangent u. I don't think it really matters. I think more students probably use the first one, but this is a calculus 1 integral. And of course, this is Lagrange method where you get the du over u. So now we see this integral here actually involves the natural log of the cosecant plus the cotangent, of course, where the argument in both cases is x plus pi over 4. And then, of course, we get the requisite negative here and the 1 over root 2. So this is a very elegant application of this particular theorem here. I usually call this a lemma in pre-cal, but it's a very important one. And if you look in engineering math books and differential equation books, which pretty much one and the same, you see this formula. And so again, sometimes we want to avoid a more difficult substitution if we can do it by easier means. And this is certainly very straightforward. So I thought that was an interesting problem that's kind of a calculus 1 problem with extra pre-cal. Now what I wanted to do, I just dressed up a few problems here that I wanted to do for you. Again, the interesting part about some of these problems is that they look odd, but they're really pretty simple. But if you look at them the wrong way, you can get off on a tangent, no pun intended, and then really just write down something that makes no sense. I mean, that's one thing about the calculus. Sometimes you have to do a double take. It's like, oh, is it really that clear, or am I thinking something else? So now what I wanted to do, I love conjugate methods, and I really like teaching algebraic methods to put an integrand in a more suitable form to actually find an antiderivative. So one of the problems looks like this. This is the integral of 5 divided by 3 e to the x minus 2. And then you think, well, that's not really du over u because that e to the x is stuck. We're stuck with it. So we're thinking, can we try some type of algebraic maneuver just like we do in identities in trig, and of course, as we do in algebra. So I tried the e to the x, e to the negative x divided by e to the negative x. So of course, get rid of the 5 for now. It's kind of in the way. And so this will give us an e to the negative x dx upstairs. And then, of course, downstairs, as we multiply by e to the x, the e to the x and the e to the negative x, excuse me, as we multiply by e to the negative x, the e to the x and the e to the negative x absorb to give you a 1. So that leaves us a 3. And then, of course, we have minus 2 e to the negative x. But that's exactly what we need because we get the copy of e to the x or e to the negative x upstairs. So now this can be our u. U is 3 minus 2e to the negative x, and then of course du, again, the negatives will absorb, and we have 2e to the negative x dx. And you're thinking, well, how nice is that? We can simply dress this up with a 2 to match that and then pay for it. So we have 5 halves, and then of course now we have du over u, which is the natural log form. So we get 5 halves times the natural log of the absolute value of 3, that is u, 3 minus 2 e to the negative x. So one of our famous formulas, which we've used many times, but again, will seep away out of our brains when we don't think about it, the natural log of the absolute value of u plus a c. That's the integral formula that fills in the gap made by the power rule, as you know very well. we don't have a simple antiderivative of 1 over x. It has to be filled in by the natural logarithm. And that's really what's such one of the amazing points about calculus, how everything just weaves together. I mean, that's why we're still studying it. And it'll always be a part of science, mathematics, engineering. It's just around for good. Now, this next problem I dressed up a little bit. I put neat example here, product of functions. I dressed up with some limits just to make it more interesting, so we get some review of some of our logarithm techniques. So what we have here is, here's what we're given. We have tangent of x, a product, tangent of x times the natural log of cosine x dx integrated from z to pi over 4. And then what I did is I wrote down some integrals here that you learned in Cal 1 once you learned the du over u, the integral of tangent right here, and the integral of cotangent. I said special integral formulas. So that's in your basic list. So you're thinking, how do we do this? Well, this is where this comes in to work. So if we let u just be the second product function, in this case, u is the natural log of cosine x, we reciprocate the argument and then multiply by the derivative, in this case, of the argument, and we get a negative sign over cosine. So du is negative tangent x dx. So we're thinking, how interesting. That's perfect. So now we're going to dress this up. This is actually this. So things get flipped around. That's why I thought this was a neat problem. So now we're going to think of the log of the cosine of x, the logarithm of the cosine of x as the u, and then of course here the du, but of course we don't have a negative here, so we put in the negative here and pay for it. So again, this is table ready. Let me put that in red. I really thought this was interesting. And then, like I say, I added a couple of limits, table ready. So if you want, you just put your 1 there, add 1, divide by the new power. So we have the negative of the natural log of cosine x quantity squared divided by 2, evaluated between 0 and pi over 4. And this is where I thought it was kind of fun to use the logarithms. So now we have negative 1/2. So we have natural log of cosine of pi over 4 minus natural log of cosine of 0. And of course, these arguments are squared. All of this is squared. So that's the thing you have to be careful of with this problem. And so now we have negative 1/2. So we have cosine of pi over 4 is just 1 over root 2. And we're going to square the log of that. And then we've got, in this particular case, we have minus the natural log of 1. So when you look at this, cosine of 0 is 1, but the logarithm of 1 is 0. So note, you know this, but just write it down. Note, natural log of 1 equals 0. So this implies natural log of 1 quantity squared is just 0. So now we can just focus on this part. This is 0. So now we've got the square here, but this is the log of a quotient. So this is just log of 1, which I'm going to use again, minus the log of the square root of 2, quantity squared, times the negative 1/2. This problem just keeps on giving. And then, of course, now, as we had before, the natural log of 1 is 0. And here, of course, the radical 2 is just 2 to the 1/2, which we can bring the 1/2 down by the power rule. So we have negative 1/2 times the square of negative 1/2 ln of 2. Well, when you square this particular part, you'll get 1/4 times the natural log quantity squared times the negative 1/2. So the final answer will be negative 1/8 times the square of the natural log of 2. I thought that was interesting, and I wanted to dress this problem up a little bit to make it more of a pre-calculus exercise. So when you do problems like this and you do problems like this, you just remind yourself what you spent a lot of time doing in college algebra and of course reviewing in pre-cal. So this is kind of a neat little problem here. So yeah, know how to do that. Now what I did, and this is just an exercise that I added, not basically, as I was looking through some of the examples, I saw this problem, but I said, I'm going to go ahead and throw this in as a preview of partial fractions. Now, of course, if this seems a little bit odd at the time, as you watch this video, don't worry about it. We're going to say more about this. I thought maybe I can make partial fractions a little bit easier if I just throw in something before we actually get to it, so it's not so in your face when we actually start studying it, because again, it's a very important integrating technique. So what we're going to do is fix a positive a, and we want to figure out what this integral is, because when you look at this, you see, well, that's just the integral of 1 over a difference of 2 squares. And of course, in physics and engineering, this is a very important integral. It comes up a lot, especially in electricity and magnetism. So what I wanted to show you was just kind of a little technique, and I'll say more about the cover-up method when we get to it. Most students enjoy what I'm doing here, but let me show you what I'm doing. And I want you to be thinking about this, so when I get to it again, you'll already be one leg up. So what we want to try to think of is, when we factor this difference of 2 squares, a squared minus u squared, can we do the backwards process? Because if you think about here, we're always adding fractions, getting a common denominator, and then moving forward. But rarely do we decompose the fraction. That's why you say partial fraction decomposition. So here's a little trick that actually is mathematically correct. If we have two distinct linear factors, then there are coefficients a and b that exist such that 1 over a minus u times a plus u is actually a over little a minus u plus b over little a plus u. So that's what we call a linear partial fraction decomposition of distinct factors. So what I want to show you here is, if this is true, and I'll say more about this when we talk about it, is we can clear denominators. So you're thinking, what would you do in a college algebra class? So you multiply both equations by a minus u, or the equation by a minus u times a plus u. Well, notice, of course, the only thing that survives here is the 1. And then, of course, the a minus u absorbs, and you're left with the a plus u. And here, of course, the a plus u absorbs, and you're left with the a minus u, lowercase, of course. And so now you're thinking, this is an equation that's true for all values of the variable for which it is defined. And then you're thinking, okay, so can I just be clever here? And this is where we get clever. We want to annihilate this term, so we let u equal a. So that annihilates this term. And so we just get 2 times, or excuse me, a times 2a equals 1. And we solve for uppercase A, 1 over 2a. We do the same thing here. If u is equal to the additive inverse of a, then this term will be annihilated. And then, of course, we're going to get b, in this case, times a minus a negative a. Again, b will be 1 over 2a. And I'll tell you about the cover-up method when I get to this. That I just wanted to make a note here. We'll talk about this soon. There are other methods to do this same process, but unfortunately, when you don't have distinct linear factors, this cover-up method doesn't work. Now we can look at this and say the original integral can be replaced with the sum of these two integrals. That is, now we can replace a with 1 over 2a, and we can replace b with the same thing, 1 over 2a. But now we're thinking, okay, we want to make this table ready. So if that's going to be the substitution, we're going to need a negative upstairs. The 1 over 2a we can factor, and of course we'll have to pay for it. Now, of course, if this is going to be the substitution, we just need the 1 upstairs. So we factor the 1 over 2a, and then of course this is table ready. Both of these are table ready. These are log forms. So now we see we get the negative of 1 over 2a times the natural log of the absolute value of a minus u, plus 1 over 2a times the natural log of the absolute value of a plus u here. And then, of course, you know, we love pre-cal. So this is just the difference of logs, which we can now write as the log of a quotient. So we have 1 over 2a times the natural log of a plus u divided by a minus u in absolute value plus a constant. So I put this in a box. Boom, right there. That is a very, very important and vital formula in integral theory because it comes up so often. And now the thing about this is that when you look at this method here, we see, oh, by decomposing this integrand into two fractions, we can actually find coefficients A and B to make this work. And so now you can just fit this in, maybe you replace A with 4. So you have 16 minus u squared and replace u squared with your favorite function. So the beauty of this problem is that via partial fraction decomposition, you get a really nice result. It's just I saw an example where this was written this way, where you knew how to do these. And I thought I'm just going to back up one and share this with them. But of course, if you look in your integral table, you might also see the integral du of u squared minus a squared, which is just the negative of this. So this is the negative of this, float the negative through. So this will just be the negative of this. Of course, minus C1, of course, call that C if you like. Now you could leave the negative out front, or you can run the negative up to the power and reciprocate. And then now you see that this integral we can get from this integral just by flipping the argument of the logarithm. So it's amazing when you see this. I mean, if you know this integral, you automatically know this using the properties of the logarithm if you want to basically absorb the negative. So something I use quite often, or we use quite often, is that when we have the log, or say natural log, or any log, it doesn't matter, x to the r, this is just r ln of x, or you can just use any base. You can just say the base a logarithm of x to the r is just r times the base a logarithm of x. Of course, a here is the natural base. So the power rule is an amazing identity of the logarithm that we take for granted. And just like determinants in linear algebra, we are stuck with logarithms because theoretically they are extremely important. So I just wanted you to look at this and think of this as a preview to the future of how we will actually study partial fractions. So I'm thinking that this might make the transition a little bit easier. And when I bring this back out, you'll be able to tell me what we derived. So I thought this, again, would be a nice preview of what's to come. All right, now we're almost done. What I wanted to do, and this is when I thought, well, let me, I'm freezing. Let me think of some trig problems that are basically conjugate methods. Now that's what I wrote here, conjugate method. I wrote it in blue and wrote it in red. So I guess I thought it was pretty important. And then Pythagorean identity. I like these examples because when we get to trig integrals, we're going to be using the Pythagorean identities over and over and over. Excuse me, and also the power reducing identities. Now, even those the particular identities don't seem that important, they are replete in calculus. And so that's why you learn trig. Again, calculus without trig, I mean, just in time trig for calculus, that doesn't work. You need to be familiar with these things. So I thought I would throw in some ideas that we're going to use quite a bit when we get to the trig integrals. So the first integral, again, this is a calculus 1 integral, but with a twist. And you're thinking, this isn't Weierstrass, like you said, just like the other problem we did. We didn't have to use the big guns. We could just use some simple ideas for trig that don't require complicated formulas. And so in this particular case, we have the integral dx over cosine x minus 1. And the first thing you do when you look at that, you're like, well, it's kind of naked. It's not really a du over u. I'm stuck with the cosine. So can we modify this just like we did with the exponentials to make this more user-friendly? And of course we can, because of the Pythagorean identities. Sine squared plus cosine squared equals 1. And that's what saves us. It always does. And so what we do is, cleverly, we just multiply this integrand by the conjugate of the denominator. And upon doing that, we're going to get a cosine x plus 1 upstairs. But now notice, We just have a difference of two squares in the denominator. So this is going to be a cosine squared minus a 1. And of course, the outer and the inner terms absorb. And so now we're looking at this and saying, well, very good, because now this is just the additive inverse of sine squared. So we can replace cosine squared x minus 1 with a negative sine squared x. And now we've got the best of all possible worlds. We can break up the fraction. So now in this case, we're going to get a cosine x divided by negative sine squared. So what we can do is do equal opportunity. I like to say spread out the sine. So we've got negative 1 over sine and cosine over sine in product. And then of course, with the second factor, with the 1, we just have minus 1 over sine squared. Well, of course, 1 over sine is cosecant and cosine over sine is cotangent. We're like, yay, that's an easy derivative with a negative sign. And then of course, 1 over sine squared is cosine squared with a negative. Again, these are easy derivatives in calculus 1. So what is the antiderivative of cosecant cotangent? Well, it's the negative cosecant. What's the antiderivative of cosecant squared? Well, it's the negative cotangent. But of course, the negatives here absorb the negatives from the antiderivative, and we just get cosecant plus cotangent plus an arbitrary constant. So you can make what seems to be a rather formidable integral into one that's simple. But again, just a lot of easy pieces. But the easy pieces thrown all together, like doing a center of mass problem, can be daunting if you don't keep the organization up. So what I like about the first section of chapter 8 is that it tries to emphasize a lot of the techniques that you learned in calculus 1. And of course, when we do the inverse trig, you'll see some of those, but you can already do those very well. These are kind of like off the beaten path. You don't really see them all the time. And it's like, well, how would I do this? Well, with that in mind, I found another one that I thought was interesting. Notice here, it reminds us quite a bit of this. So you're thinking we could deal with the secant or we can get rid of it. And what I did was get rid of it. So my deal is make it as simple as possible, but there's a million ways to do problems. So trig identities open the door to that. So what I first did, we've got 2 divided by 3 times the difference secant x minus 1. Okay, or the difference of secant x and 1. And so, of course, the 2/3 is in the way, so we get rid of that. And then I'm thinking, they're like what we had up here. Let's do sines and cosines. So I write the secant as 1 over cosine x. And then, of course, we multiply and divide by cosine x, which I kind of did in my head here. But at this point, if you want to do cosine x times the cosine x, and of course, this is inside right over here. I just didn't have room for it, so it would be right in there. It's certainly not on the outside. That doesn't make any sense. So of course now you would see that the cosine would absorb, leaving you a 1, and then the negative 1 times the cosine, and then upstairs a cosine. So now we're making it look just like this, just with a small adjustment. So I thought, well, if I work this problem like I work this problem, it'll make it easier. So now, of course, moving from here to here, we're going to do the same thing we did up here. We're going to do the conjugate method. We're going to do the conjugate of 1 minus cosine x, which is 1 plus cosine x. And so multiply and divide by that expression. And so now when we do this, just like we did upstairs, it's more user-friendly. We'll get the 1 minus the cosine squared, but upstairs we'll get a cosine x plus a cosine squared. But of course, we get the additive inverse of what we have here. So this is just sine squared. This equals sine squared. Nice Pythagorean identity. And so now we've got the 2/3. So we have cosine divided by sine squared. And then of course we have cosine squared divided by sine squared. So we're getting the same thing basically. So now we've got the 2/3. Now equal opportunity. So we have 1 over sine x times cosine x over sine x. But now note we have cotangent squared. Cotangent squared. And this is where you have to remember, we don't use this one as often. We have 1 plus cotangent squared x equals, in this case, cosecant squared. So if we want something we can integrate, we just substitute if and only if cotangent squared x equals cosecant squared minus 1. So often we want to get ourselves back to something like this, which we know. When when you're doing this the first time, oh yeah, cotangent squared, I know the antiderivative. No, you don't. You know it if you do this. And that's what I think is interesting about this problem. So now, of course, the first integrand will be what? Cosecant times cotangent. And then, of course, for cotangent squared, we just replace that with cosecant squared x minus 1, like I did here. Of course, we still have the 2/3. And now we're back to what we were up here. The antiderivative of cosecant cotangent is just negative cosecant. The antiderivative of cosecant squared is the negative cotangent. And of course, the antiderivative of -1 is negative x. So if you go ahead and rig this in terms of cosine, then it looks exactly like this. And the problem's a lot easier. These Pythagorean identities we will use over and over. And this type of manipulation with the trig functions, the cosecant squares, the secant squares, all of that stuff, we will do. And we'll have to think about the origins in calculus 1. It's like, wait a minute, did I get that right? So what I often will do with my students, they'll say, let's write down this derivative formula and work it backwards. Oh, we do know that antiderivative. So you really always have to test yourself and make sure that you're writing down something that's actually correct and not nonsense. And so now, of course, if you like, you can factor the negative. So we get negative 2/3 times what? Cosecant x plus cotangent x plus an arbitrary constant. So what's interesting about section 1 is that it's not overly hard. But what I've tried to do is to bring out some ideas that maybe get forgotten. And of course, you're so busy in Calculus 1 trying to finish the class and doing substitution that you don't get into maybe more of the more interesting little subtle adjustments that you can make with integrands. Unfortunately, a lot of times you forget these ideas and you try to throw some advanced technique onto the problem when all you need to do is something like this. So that's why you learn very quickly that the process of anti-differentiation is much more difficult. You do have to think about it, and you have to be a lot more resolute in what you do. Shoot, when we're doing the applications, even though the integrals don't tend to be very difficult, they are filled with algebra, and just a slight little error or problem, where you're not quite sure about the moving forward can be catastrophic to the problem. It's like missing the fact that you have an odd function integrated on a symmetric interval. I mean, sometimes we just have to be a lot more observant. So I hope this was helpful. Again, I wanted to focus on some more center of mass problems. And of course, that work problem that a colleague of yours asked about, I thought it was a really nice problem and of course a valid problem. And then to acquaint you with some of the more refined techniques that you would have learned in Calculus 1, but of course probably got kind of rusty. So you won't have to spend much time on section 1 of chapter 8. I guess you'll probably spend more time on the center of mass. But again, the center of mass is quite intuitive, where we don't have that intuition, excuse me, in the work problems. We certainly have it with the center of mass because that's kind of part of our reality. Moving liquids around it, again, that's more infinitesimals to the point that we have to treat it separately. But again, when you think about it, some of the center of mass problems can be more difficult because of the moments. But you decide what you think is the truth. And as you learn this, share your ideas with your friends. Okay, so the next time we meet, it'll be next week. And of course, we'll start talking about integration by parts, which I think you'll find to be extremely interesting, as Professor Ron says. Well, everybody, I wish you well. I'm so glad that we're back online, that we have power, that we can enjoy a warm night's sleep. So bless all of you, and I'll see you again soon.